So this is question number 7, and this is about ranking nucleophiles. So what I think people had a hard time with here was a lot of times you'll see the CH3COO, and you might not know what that means. What that means is the COO means this is that C, there it is double bonded to one oxygen and single bonded to another oxygen. Right? Do you see that? It's called a carboxylate. We also have, so we have 5 things here. S minus, O minus, alcohol, carboxylate, and carboxylic acid. And they're asking us here to rank the nucleophiles. So we've talked about different things about we want a nucleophile to be reactive, right? So the reactivity of the nucleophile. So which of these do you think is the most reactive? The most willing to give up its electrons? Well, let's take a step back. Well, maybe just look at these things. So 2 of them have charges. 3 of them have charges, 2 of them don't. Do the charged nucleophiles going to be more reactive than the uncharged ones? Yep, so we can at least write negatively charged nucleophiles. So then we have an S minus, O minus, and an O minus. So what's S versus O? Where are they at in the periodic table relative to each other? They're on the same column, right? What happens? Is S bigger or smaller than oxygen? Bigger, right? It means its valence electrons are farther from the nucleus. They're going to be more willing to react. So the S one, this is going to be number 1. What about oxygen versus oxygen? What's the difference between these two? What can this one do that this one can't? This one can do resonance, meaning that its lone pair can be tied up doing something else instead of reacting. So which one's going to be more reactive? This oxygen or the one that can do resonance? The one that can or can't do resonance? Can't. Very good. That means this is 3. That makes sense, right? Still a charge. But now what about these two? Again, we're looking at what? We're really looking at the lone pairs on these things. Which lone pair is more reactive? The alcohol or the carboxylic acid? Well, here if you're confused, are acids nucleophiles? Are acids electron rich or electron deficient? An acid. Electron deficient. Remember, H plus is an acid. This is called what? A carboxylic acid, right? Also, this lone pair can do what? It can also do resonance, so it's going to be less likely to react in this case. So 4 and 5. So for number 11, they're asking you for the product here. But one of the biggest things I want you to start doing is recognizing how to determine this. So there's 2 reactions at this point. We know SN1 and SN2, right? So the first thing you ask yourself is, what kind of alkyl halide or electrophile do I have? So what kind of alkyl halide or electrophile do we have? Primary, secondary, or tertiary? It's primary. Everybody needs to see this all the time, right now. This leaving group is bonded to a carbon that's bonded to 2 hydrogens. It's bonded to 2 hydrogens, that's primary. If it's bonded to 1, that'd be secondary. If it's bonded to none, that'd be tertiary. Okay? So if it's a primary alkyl halide, can we eliminate one of these, SN1 or SN2? We can eliminate SN1. SN1 can't have a primary alkyl halide, and we're going to learn about why that is, right, as well. So this has to be an SN2 reaction. What do you know about an SN2 reaction? How many steps? 1 step. How many arrows? 2 arrows. 2 arrows. Is there a carbocation? No. What about the geometry? Where does the nucleophile have to go? Nope. The nucleophile needs to go 180 degrees away. Why? Because where is sigma star? 180 degrees away from the opposite side. This is the sigma bond. Sigma star is 180 degrees away. So the nucleophile has to go to the back side. Now, does this carbon have an asymmetric center? Is this sp3 hybridized bonded to 4 different things? No. So it doesn't really matter. We're not going from R to S because we never started with R or S. But we still need to draw our arrows such that we show that it's going to this back side. Did anything happen to these 2 carbons here? Nope. Are they still there? Yep. How many carbons were on the bromine? There were 3. This one's bonded to the sulfur, which was bonded to 2 carbons. We balance our charge, Br minus. Right, 1, 2, 3. 1, 2, 3. Sulfur is bonded to this carbon that was attached to the leaving group. Sulfur had these 2 carbons there. Nothing changes there. Classic SN2 reaction. In an SN2 reaction, if we looked at the nucleophile, what kind of nucleophile do we want? Do we want the nucleophile to be reactive, or do we not care about the nucleophile for SN2? We do care, right? Because what's the rate for an SN2 reaction? Rate equals K, concentration of the electrophile, times the concentration of the nucleophile, right? So we want a reactive nucleophile. We want a nucleophile with a charge, negative charge, right? Nucleophiles are electron rich. We want the nucleophile to be skinny, right? So those are all the things we want to look for. What kind of solvent would we want here? Polar aprotic. Somebody give me what's an example of a polar aprotic solvent? Acetone. Aprotic, right? Acetone. What about DMSO, DMF? Things without, anything without OH, NH, SH, or pH. You do not want polar bonds to hydrogen. Aprotic, right? You have it listed in your notes. So this one asks for the major product here. First thing you gotta identify is what kind of reaction is this gonna be? So the first thing I always ask myself is what kind of alkyl halide do I have? What type of alkyl halide do I have here? So the right tertiary alkyl halide. That eliminates one possibility. Can it be SN1 or SN2? So I'm gonna write SN1, SN2. Which one does it eliminate? SN2, right? The sterics. SN2 can't have a tertiary alkyl halide. It can't do the backside attack because of sterics. So that means it has to be SN1 in this case. In SN1, what happens? What happens in the stereochemistry of SN1? You get racemization, right? Now, do we have a stereo center here? Are we starting with an asymmetric center? Is there something that's sp3 hybridized bonded to 4 different things? No. So we don't need to really worry about it. But the first step is going to be what? In an SN1 reaction? Leaving group leaves, or in this case, the first step, not always. Leaving group leaves. What's that going to create? A carbocation, right? Carbocation. That's going to be the slow step, right? Making a carbocation slow. Why is making a carbocation slow? Because you're not having a full octet, right? Not having a full octet. What's going to react next? Remember these reactions? They like the polar protic solvents, the solvents with the OHs, the NHs, the SHs, and the pHs. This is called solvolysis. The solvent reacts. The solvent is the nucleophile. So here comes the solvent. It's like an addition reaction. Solvent adds because it's the nucleophile. Right? So overall, this reaction is going to be a substitution, but there's going to be different steps along the way that aren't substitutions. Does that make sense? The overall reaction is a substitution, but we're going to have different steps along the way. So this is an addition step. We overall had a plus charge in that step. Did anything happen to any of the H's on oxygen? Did anything happen to these hydrogens? Are they still on that oxygen? Yep. So what? I made an oxygen-carbon bond, but if I balance my charge? No? Where's there need to be a plus charge? In the oxygen. And then the last step is going to be a proton transfer, a little deprotonation. The proton just falls off. And so we made H plus all along the way. Y'all see when the hydrogen falls off, it lost all its electrons, right? So now you have an H plus to balance your charge. How many electrons are in this bond? Those 2 electrons right there in the bond go to the oxygen. right? And we end up with an H plus to balance our charges. Do we need to worry about wedges and hatches here? No, because there's no asymmetric center to start with. So it's just a classic SN1 solvolysis. Oops. Where did the BR go? As an organic chemist, I'm constantly not caring about things that don't have carbon. The bromine's just there. It's still there. It's always there to make sure we balance our charge. Good call. You got the Br minus is there. You could show, if you feel like you want to have the Br grab the H, you can. You don't have to. The H just really just falls off because H plus and Br minus, bromine doesn't, it fully dissociates. But yes, bromine's there along the way, balancing our charges. Good call. So for this one, again, SN1 or SN2. The first thing we're going to look at, what type of alkyl halide do we have? Primary, secondary, tertiary, allylic, or benzylic? What kind do we have here? Tertiary. Got to be able to see that right away. Tertiary because the carbon or the atom the leaving group is attached to has no hydrogens. So that's tertiary. So that's going to be very sterically bulky. So which reaction does that eliminate? It eliminates SN2, right? Because you can't get the nucleophile on the back to the back side. So this is easy, it helps us. But also, and I'll always write this, I'll always tell you, if something's a solvent, I'll tell you it's the solvent. There's no reason to hide that fact. But in this case, this nucleophile, the solvent, is polar protic or aprotic. What do we have here? Protic, right? Water. So that also tells us SN1. Does the SN1, do SN1 reactions care about the nucleophile? No, because what's the rate for an SN1? Only determined by the concentration of the electrophile. So SN1 doesn't really want a reactive nucleophile, right? So what's the first step in this reaction? All right, the first step is going to be the leaving group leaves. Leaving group leaves. All right, the leaving group left. That's going to be a slow step in this case because what are we forming? What's the product of this reaction? A carbocation. Why is a carbocation unstable? Doesn't have a full octet, right? The octet rule. So that's going to be a slow step. What's the next step? The next step is that the nucleophile adds. And in this case, the nucleophile is just the solvent. Right, which is just the solvent. Now remember, take a step back. Did we start off with, is this molecule, is there an asymmetric center in this molecule? The carbon that has a leaving group? It is RRS. Do we care if it's RRS right now? I don't care. But we need to recognize that it is RRS. Because once we make a carbocation, that carbon becomes planar, which means it becomes flat, which means it's now a carbocation, which means the nucleophile can come from the top or the bottom. That means we're going to get what kind of products? So remember that word? We're going to get racemic mixture products. We're going to get 50% S and 50% R. So even though we start out with 100% of one, we're going to get, the water's going to come from the top and the bottom. And what that means is you need to draw both stereoisomers. So this is one way you could do that. There's one. And there's the other. You're going to make both of those, right? You're going to make both of those. So you will get two products here. And then the last step is just a proton transfer or a deprotonation. It's the same either way. It's just the hydrogen falling right off. You can think of the hydrogen just literally falling off. And I think all they want for the answer is those two things drawn out. They want you to show that you know it was both R and S products that are made, right? So you need to draw both of those. So there's two ways for a leaving group to leave. The easiest one that you recognize is that you have an alkyl halide, like a bromine, an iodine, or a chlorine, and the leaving group just leaves, right? There's another way that can happen though too, right? And the other way is through protonation. So in this case, the first step here is actually a proton transfer. And so what that's going to do, it's going to make this alcohol a better leaving group, right? Because HBr is an acid, right? Are acids electrophiles or nucleophiles? Electrophiles, right? Think about H+. Things with plus charges are not nucleophiles. Nucleophiles are electron rich. So what happened here, it turned because is OH minus a very good leaving group? Is OH minus stable? No. Is water stable though? Yeah. So check this out. So what happens after that OH gets protonated, right? All of a sudden that's a much better leaving group, right? See that? Is that a much better leaving group? But again, we ask ourselves, what kind of electrophile do we have here? Is it primary, secondary, or tertiary? So look at the carbon. So this is our leaving group. This carbon, is it bonded to any hydrogens? So is it primary, secondary, or tertiary? Tertiary. All right, so this is tertiary. So we have two options, SN1 or SN2. Which one's it going to be? It's going to be SN1 because we can't have, it's too sterically bulky. Can't do an SN2. So what's the next step is going to be that the leaving group leaves. All right, leaving group leaves. So you make water, and the Br minus is still floating around too. Then it's the same thing as happened before, right? The bromine can come from the top, or it could come from the bottom because carbocations are planar. So you'll get both enantiomers. You'll get both the bromine, the molecule R and the molecule S. So just like before. All right, so this would be the nuke adds. And you'll end up with bromine there, and the bromine here. You get both enantiomers the same as before. So this one, again, now they're kind of asking you to compare rates of reactions and what type of reaction it's going to be. So again, let's go through the process. The first question we ask ourselves, is it SN1 or SN2? All right, and so how do we determine that? We first look at the alkyl halide, right? We look at the thing with the leaving group. We ask ourselves, is it primary, secondary, tertiary, allylic, or benzylic? So in both these cases, what is the alkyl halide, or the electrophile? Primary, secondary, tertiary, allylic, or benzylic? It's primary, all right? I agree. They're both primary, right? So what reaction must it be? SN2, because we can't have primary carbocations, and we'll talk more about that. Okay, if it's SN2, then what's different? Is the nucleophile, now we're going to look at the nucleophile. What's the nucleophile in both cases? F minus, so that doesn't change, nothing to compare there. What about the solvents? That's the last thing to look at. The bottom one has a polar, what kind of solvent is this one? Protic, and both DMA and DMSO are aprotic. I'm never going to ask you to memorize what it looks like. I'll draw the structures out and I'll tell you it's a solvent. But if I draw the structure out, can you tell if it's an OH, an NH, an SH, or a pH? I hope so. You'll be able to tell if it's product or aprotic, right? So for an SN2 reaction, what reacts faster? What's a better solvent, protic or aprotic? Aprotic. So this rate should be faster, right? They're both SN2 reactions, but the top one should work better because, right, it's the same electrophile, it's the same nucleophile. The only difference is the solvent, right? And for an SN2 reaction, right, do we want the solvent involved? No. So we don't want, right? So so if the solvent's not involved, that'll make the reaction go faster. Yep. So for this one, for 26, there's a little thing here you have to know about D. Does anybody know what D stands for? It stands for deuterium. It's hydrogen with an extra neutron. An extra proton is something else. An extra. Oh. So this one has a deuterium, which is essentially heavy hydrogen. So it's hydrogen with an extra neutron. So it's basically the same size as hydrogen, though, so it's not very big. So the question is, again, first thing you ask yourself in all these reactions, right? So I like to draw out. I'll start drawing out SN1, SN2. Those are the two reactions we've learned. What kind of alkyl halide do we have? Primary, secondary, or tertiary? Allylic, benzylic. Primary, right? Treat the deuterium like a hydrogen. So this is a primary alkyl halide, right? If it's a primary alkyl halide, what kind of reaction can it not be? SN1. SN1, you can't have primary carbocation. So we know the reaction is going to be SN2. SN2 has how many steps? One step. How many arrows? 2 arrows, right? So you know that already. Just boom in your head before you even look at this. The nucleophile, right? If you take a look at the nucleophile, is it reactive? Yes. Do we want a reactive nucleophile in an SN2 reaction? What's the rate law in an SN2 reaction? Rate is equal to K times the concentration of the electrophile times the concentration of the nucleophile. Oh, we do want a good, right? This is for SN2. We want a reactive nucleophile because it's in the rate determining step. We want it to be reactive. We want it to have a negative charge. We want it to be skinny, right? Because we need to do the backside attack. All right, so what's going to happen here? Drawing some lone pairs. We're going to go to this carbon. And notice how we came 180 degrees away, right? Because that's where sigma star is. Came 180 degrees away. Do that SN2 reaction. Remember, we get inversion. So I'm not sure if this is RS. It doesn't really matter. They're not asking us that. But if this was R, now it became S. Do you need to draw your arrows such that it goes to this side? Yes, you do. Your arrow needs to show that it's coming from the 180 degrees away from this. And why is that? Because where's the sigma star? Where's the anti-bonding orbital at? It's right there. Right? And we talked about that inversion and why that happens. All right, so for this one's challenging for a couple reasons. You got to recognize there's 3 things in the mixture here, which kind of throws things off. Usually you're used to having 2 things and kind of deciding. But here you have 3 things. But hopefully you can identify the electrophile right away. What is the electrophile? The thing with what on it? You got 3 species. You got the ring, you got the sulfur, and you got the sodium hydroxide. Which one's the electrophile? The ring. This is the electrophile. And these 2 things are not. What kind of electrophile do we have? Primary, secondary, tertiary, allylic, or benzylic? What kind of electrophile do we have? The carbon that the leaving group is bonded to has how many hydrogens attached to it? 1. Is that primary, secondary, or tertiary? We've agreed it's a secondary. So does that mean SN1, SN2? Which one does it mean? Can we eliminate any of them? Nope, can't eliminate them. Darn it. Okay, so the electrophile didn't let us eliminate it. Now we want to look at the nucleophile. So if we see something with a negative charge, if you see something with a negative charge, you know it's going to be SN2. Right? It can't be SN1. SN1 wants to have a carbocation. You're not going to have a negative charge with a carbocation. Are there any negative charges here? So this is where it gets a little tricky. There is. Anytime you see Na, lithium, magnesium, or potassium, if you see those four molecules, where are they on the periodic table? Or four atoms? Where are they on the periodic table? On the far left. These will always be cations. If you see them bonded, the thing they're next to has a negative charge. Always. Write that down. Magnesium, potassium, sodium, and lithium. They're bonded to something. Even though it looks like it shouldn't have a charge, it has a charge. So because we have this OH minus, that's a dead giveaway that it can't be SN1 and it has to be SN2. All right? So we have a negative charge that makes us think SN2. It's good. But there's a little bit of a trick here. What's going to react faster? Is this OH minus going to do the substitution faster? Or is it going to deprotonate this faster? It's going to deprotonate this faster. Right? And why is it going to do that? Because now it's sulfur. What's more stable? S minus or O? Or actually, what's more stable? S minus or O minus? Right? So it's going to make that S minus. And the S minus is what's going to react with the ring. We said it's an SN2 reaction, so it's got to come from the backside. All right, like that. So you see that? So that chlorine is dashed. That means the nucleophile had to come from the top, right? You all see that? If the chlorine is pointed down, the nucleophile had to come from the top. Because where's 180 degrees away from the bottom? The bottom's this way. The top would be 180 degrees away. So what's going to happen is inversion. So what's that going to look like? So nothing changes over here. But over here, the H is now down. And this sulfur that had to come from the top is now pointed up. And we've lost the Cl minus. Do you see that? Right, you deprotonate here. The sulfur becomes the nucleophile. SN2 reactions need to come from 180 degrees away. Right? And it's going to pop this open. So if the leaving group was pointed down, the nucleophile had to come from the top, so the nucleophile would be wedged. Do we see that? So for these ones, for this one, we got to look at, let's figure out what we have here first, SN1 or SN2. So we look at what type of alkyl halide do we have here? Primary, secondary, tertiary? Secondary. Does that eliminate anything? Nope. So now we're going to look at the nucleophile or the solvent. So in this case, the solvent is water. Is that a very reactive nucleophile or unreactive nucleophile? Water. Is water reactive or unreactive? Unreactive. So does that make you think SN1 or SN2? SN1. Because SN2 wants a reactive nucleophile, right? Things that are charged. So okay, now we're thinking SN1. Good. Perfect. So what's going to happen here? The leaving group's already there. We don't need to do any protonation. So the first step in this case is going to be that the leaving group leaves. Right? Leaving group leaves. Now, one thing we're going to learn about carbocations, or we should know about carbocations, is that this is a secondary carbocation. And carbocations will rearrange. They want to become more stable. All right? They want to become more stable. So carbocations want to become more stable, so they want to become tertiary because they have more hyperconjugation. So there's 3 ways to stabilize a carbocation: lone pair resonance, pi bond resonance, and hyperconjugation. So if we look for these sigma bonds that are 1, 2 bonds away from the carbocation, those are the bonds, the atoms, that can shift, that can rearrange. So what's going to happen here is this hydrogen is actually going to take its 2 electrons and leave that carbon. So this is a rearrange, an H shift we call it. So what happened? 1 carbon lost a hydrogen, 1 gained a hydrogen. So if we go 1, 2, 3, 4, 5, 6. Which carbon lost a hydrogen? 3 did. All right. Carbon 4 got a hydrogen. Charges don't move. Atoms and electrons move. All right. The mistake people make is they say, oh, the charge moved. No. Charges don't move. Electrons move. Electrons and atoms move. Plus charges don't move. So 4, it had a hydrogen already on it. If you look at carbon 4 right now, how many hydrogens are on carbon 4? 2. And there should be a plus charge on 3. So we went from a secondary carbocation to a tertiary. How do I know it's tertiary? Because 3 has no hydrogens bonded to it. So we call it a tertiary carbocation, and that's more stable. Now chlorine comes in. Right? The nucleophile adds an addition reaction. Do we need to worry about wedges and dashes? No, because there's no asymmetric center. So that would be the product.